give a keynote talk at PODC. So couple of decades or maybe 15 years ago, I was sitting in a conference in the US. Those were the days where people badly wanted to go and live in the US. By the way, one of the problems with this kind of conference talks on Zoom is that you don't see when I'm smiling. Something when I smile, it's a joke. So please don't take things personally. So 15 years ago, I was sitting in a conference in the US. I lived there, and I'm happy to say hi to Sven Holund and Nancy, whom I see among the participants. And in that conference, there was a keynote. And the keynote speaker was a Turing Award winner, a real keynote. And he was basically talking about bad ideas in computer science. And he was giving examples of which ideas were bad. Somehow ideas that people thought would be good and turned out to be bad. And in fact, now I cannot move, I'm sorry. This is something that's, okay, good. And the first example he took was distributed computing. So the first example given by that keynote was that distributed computing was a bad idea. In fact, people were investing time, wasting their time in this discipline, and there was practically no application where more than 3 nodes, processes, computers, whatever you call them, would share a state and communicate. And I was pretty shocked because I was working on distributed computing, working with Nancy, working earlier with Sven and other people in this discipline. Obviously, in retrospect, that keynote speaker was wrong. Of course, he was right in many things, but not on that aspect. Distributed computing was not a bad idea, and we can see it today. All over the place, maybe arguably all interesting applications are distributed. Either they are distributed because the program is connected to other programs all over the world through the internet, or the program itself is distributed on a bunch of multiprocessors. So he was wrong. It's a he. He was wrong. He was wrong that distributed computing was a bad idea, and he was wrong that it was basically a failed discipline. But still, the question whether the distributed computing research was somehow failing, it's more questionable, and this is what I want to talk about a little bit today. And it seems to me that if we think about distributed computing research, and what I mean by distributed computing research, I really mean the principles, things are not that clear to me. What I want to say here is that the fact that distributed computing is all over the place and everybody's doing distributed computing in all conferences, in all kinds of industries of computing, might not be a great sign for distributed computing research. Let me explain a little bit what I want to say. Clearly, most innovations, in my opinion, are coming from engineers. They're coming from industry or from Monsieur Tout le Monde, as we say in France. Many innovations are not coming from academia. And one of the explanations is precisely because of the industry of computing is very vibrant and computing is mainly distributed. So a lot of people with a lot of money, big groups, they are much faster than academics. And here I associate the word academic with doing principle of distributed computing research. But there is another reason, is that academics are basically busy writing papers because they need to be promoted and they need glory or whatever. And here there is this problem of relevance. When we write a paper, we want our paper to be relevant. And relevance here means relevant to the reviewers of our paper. And I don't know about you, but I observed this tendency that conferences, at least in theoretical conferences, tend to consider relevant papers that tackle problems that have been posed in an earlier edition of the same conference. So typically a problem opened in an earlier edition is considered relevant. When you come and you close the problem, nobody will tell you that what you were doing is irrelevant. And even if you go to practical or system conferences, when what is considered relevant usually are problems that are considered interesting for industry, which means problems that have been already posed and discovered in industry. So somehow the word relevance tend to be against the very notion of innovation. And of course, I'm caricaturing a little bit, but still, I think there is some truth in that. So there is a risk that by the success of distributed computing could go with distributed computing research, at least the principal part of it would somehow slowly disappear and be cast away. What I mean here is, and let me give you an example I have lived myself. I used to do research some time ago before discovering distributed computing in object-oriented programming. And at some point that was very, very hot because Smalltalk and all those languages, Simula were great. And a lot of people would go there and do research because that was a hot topic. But then everybody ended up doing object-oriented programming. So somehow all disciplines became object-oriented in computer science. So the conferences almost died because the research was mainly about
Rachid?
Yes, sorry.
There are a request for you to start your video, if possible.
To start my video, sure.
Yeah, concurrently with sharing your screen.
Yes. Okay,
thank
good. You. Here I am. So I was saying that some time ago I was doing research on object-oriented programming, and the conference there were ECOOP and UPSLA. And when object-oriented programming became mainstream, the conferences, let's put it in a very politically correct way, lost their prestige. And lost their prestige to the point that they almost disappeared. Of course, some smart people could save them by doing some interesting, by having some interesting approaches, but that's a risk that we end up in the PODC disk community being somehow isolated from the interesting problems. So of course, nothing fundamentally wrong with getting lost in an island that is beautiful, and we can still work in our island and work on interesting problems like weakest failure detectors or local model or conject model, or what have you. I mean, we can prove to each other that we are smart and work in those areas. But I think we can do that when we get close to retirement. But for our students and for young generation, who need funding and need promotions, I think it's risky, very risky. So one of the messages of my talk, and if not the main message of this talk, is really to try to do something about that. So of course, this is very, I mean, pretentious to say road to salvation, but just a suggestion of one road to salvation. And Jean Cocteau, I didn't know how to translate that precisely, but a poet, a French poet, said, puisque ces mystères nous dépassent, feignons d'en être les organisateurs. I could translate it by saying, given that these mysteries are beyond us, let's pretend that we organize them. What I'm trying to say here is that those innovations that are coming from industry are somehow beyond us, and they sometimes look like mysterious for us. But let's at least pretend to organize them or to have been behind them. Of course, that's not what I mean exactly, but I'll try to explain what I mean. And there is no, so what I'm suggesting is really to look at what industry is doing and what people are doing. It's not necessarily industry. Sometimes it's just random people who discover some great ideas like Nakamoto or others and come up with the great ideas in distributed computing. So the suggestion here is really to look at that, to be curious and look at those innovations and maybe try to take them and dive with them to the center of distributed computing, understand them, dissect them, and maybe improve them. And there is no shame in doing that. There is no shame in doing that because we can do that successfully. We have a language of precise abstractions that could help us do that. And there is no shame in doing that because if we look at our own history as a community, I think this is what people have precisely done. If I look to the first transactional systems and the celebrated FLP paper, if you read FLP paper, and I see that I think Michael and Nancy are among the attendees, if I'm not wrong, the introduction of the paper talks about a transactional monitor and the problem of distributing transactions and making them agree on something. So the motivation was definitely coming from industry and some discussion with Gérard Lelanne. So there is no, it's not considered, I would say, a shame to start from a practical system and crystallize the main problem through something like consensus and prove when it's possible and impossible. There are other classical examples. If we look at the notion, the very notion of Byzantine failures and the Byzantine generals, again, I hope Leslie will not contradict me, but it dates back to the SIFT system when NASA tried to build a computer system for airplanes and started thinking about that problem of reaching agreement in the presence of weird failures, Byzantine failures. So again, it all came from industry. If we look even earlier to the mutex problems, which somehow were originally led to what we use about, what we work on today, like atomic registers, register transformations, atomic memory, linearizability, etc. It all came from hardware and the first multiprocessor operating system by Dijkstra. And I think it's not surprising to see that Dijkstra was somehow proposing this idea of trying to clean what industry came up with. So this is what I'm suggesting here. And I'm saying that there is no shame in doing that. I think we should do that and try to do that because we have the abstraction and language to do that. And I will consider a few examples during the rest of this talk. One example is something that I have been working on with colleagues and students, and I will mention other examples I also have been working on with students and colleagues, but I'm sure there are tons of examples. I can name some, but I'm pretty sure most of you have been, at least some of you have been working on these examples. So the examples I'm going to consider is the distributed payment problem, also called the Bitcoin problem. And something is I find interesting here, very, very interesting. It dates back to an interesting, well-written paper, the paper by so-called Nakamoto. And those of you who didn't read the paper, I really encourage you to do it, even if you're not working on this kind of problems, because the paper is, I don't think the paper could have made it neither to PODC nor to DISC or SOSP or OSDI for the reasons I mentioned earlier, but it's an interesting paper. So the paper came up with a way to implement distributed payment in a peer-to-peer manner. And of course, it had some great ideas, but the implementation had some problems. So people started revising the way the protocol was designed and came up with alternatives. So today we have, I would say, thousands of ways to implement distributed payment. And one common characteristic of all these implementations, in my opinion, most of the implementations, they are very complex. They are very complex and hard to understand. And I think this is the first place where distributed computing can help, at least understand what's going on. And this is something this is a project we undertook with some students and some colleagues. The first question that we asked, and it seems to me that the first question one would ask in doing distributed computing is somehow the analog of the question you ask when you do classical computing. When you do classical computing, you ask whether your problem is P or NP. I think in distributed computing, one of the very first questions you ask is whether the problem is synchronous or asynchronous. Can you solve the problem without making timing assumptions? You would call your problem asynchronous. If you need some timing assumption, you would call it synchronous. Of course, the distinction came from the fundamental distinction of FLP paper. Is payment an asynchronous problem? If you read the papers since the very first one by Nakamoto, or whomever we call Nakamoto and others, you might believe that the problem is a synchronous problem. Why? Because the paper talks about consensus here and there, and the alternative papers talk about consensus here and there. And we know that consensus is not an asynchronous problem. You need some synchrony assumption to solve it. But you still want to ask this question here because nobody really asked the question. And as Tyrone Lannister said, to really understand the distributed computing problem, bring it to shared memory. Okay, here, as most of you know, we in distributed computing have been classifying the world into two categories: shared memory and message passing. So typically the Bitcoin protocol that I mentioned was posed in the message passing world. Processes, machines communicate by exchanging messages. But there is the alternative model that I mentioned earlier, which somehow reflects the world of the infinitely small, where processes share memory. Usually in the message passing model, it's common to consider that there is some entity called an adversary who will try to corrupt your messages or pretend to be someone else, depending on the model. In the shared memory, usually you assume that you have an adversary who's simply trying to slow down the computation. It's not trying to corrupt your messages. So that is a distinction between the two models. Of course, one could alternate the two adversaries, but this is how people have been thinking about these models. So the message passing model, people communicate by sending messages, and there is this really, really bad devil. In shared memory, processes communicate by reading and writing in atomic registers, and we assume that things can be slow, arbitrarily slow. Process P1 can take an arbitrarily long time to write something, and therefore when process 2 comes to read, we don't know whether P2 will be able to read what P1 has written, and we don't know how long P2 should wait. So this is the game we usually play in this world. It turns out that one of the fundamental results in distributed computing, and these are the kind of abstractions and language and results I'm mentioning, is that the two models are equivalent. Although they might seem completely different, they are actually equivalent. They are equivalent modulo some assumptions. You have to assume that in the message passing model, a certain number of nodes do not fail. They are not controlled by the bad guy on my left. So these two models are equivalent, of course, modulo something. And this is very important because if we want to ask the question whether a problem is asynchronous or synchronous, it's much easier to do it assuming the shared memory model because it's simpler to reason about, and especially the adversary is somehow weaker. So is payment an asynchronous problem? Now we can ask this question in the shared memory model. In the shared memory model, the problem are defined as object. We define them as in object-oriented programming. We have a state and a set of operations, and we want this object to satisfy certain properties. We want them to be atomic, and we want their implementation to be weight-free. For some of you, these are trivial things by now, but for many people, these things are not trivial at all, especially outside this community. And taking a problem and defining it in these terms is already a contribution. So doing this exercise is something very helpful. So before asking the question of the payment object, so the payment object is the object implemented by the Bitcoin protocol of Nakamoto and the 1,000 implementation or alternatives, let me take something that looks similar but simpler to precise this question of asynchronous versus synchronous. Take the counter object. So here, the goal of the object is simply to count. So it's a state with two operations, increment and read. And the goal is to maintain an integer x initialized to 0. Operation read returns the value increment. So this is an object, and you can ask, is this problem synchronous or asynchronous? So of course, it's asynchronous. It's asynchronous in the sense that we can have an algorithm where we don't have any timing assumption. We don't need any timing assumption to implement the object. We use the shared memory. More specifically, we use pieces of the shared memory called registers, and we implement the object. For those of you who have been working on this, this is trivial. For those of you who have not been working on this, you can look at the slide later, and in a couple of minutes, you will realize, oh yeah, we can do counter with registers. If you slightly modify the object and add one operation, let's here add an operation decrement. So in the previous counter of object specification, we just had increment and read. If you add an operation decrement, and if you say, I would like to be able to remove 1 if the state is strictly superior than 0, then I have this new object called counter star. And you can ask again the question, is this synchronous or asynchronous? And I guess you see what I'm leading to. This object is asynchronous, and the way you prove it is by showing that if you implement this counter star object, you can implement consensus. Intuitively, you can have two processes, one of them using the fact that you can decrement if the state is strictly superior to 0, and you cannot, if not, to somehow break symmetry. So you can implement consensus. And we know by FLP 85 and its shared memory variant that you cannot solve consensus, and therefore you cannot implement counter star. This is amazing. For many people who don't know this business, this is amazing. Of course, if you know this business and you have been using it, you're not surprised. But believe me, doing this exercise with people who make innovations in distributed computing sometimes impress them. And this is important because now we go back to the payment object and we try to define it precisely. And we say, what is really payment? Payment is transferring amount X from object A to object B, or process A to process B, if A has enough money, if has more than X. Important, only the owner of A invokes the payment. So Alice can send money to Bob, X amount of money, if Alice has enough money. And the question now translates into, is this object asynchronous? Can we implement PO asynchronously? In fact, we can ask even a more general question. What is the consensus number of this object if it turns out to be non-asynchronous? I will come back to that later if time permits. It turns out that the answer is, yes, this object is asynchronous. And this can come as a surprise because if you read the thousands of algorithms implementing payment, they all seem to need some synchrony assumption. In fact, if you know the distributed computing literature, and here in particular the work of Rachid et al., then you know that there is this object that is very powerful called the snapshot, where you can actually, in an indivisible point in time, take a picture of the entire state of the system. So this object has two operations, scan and update, and processes can update it, but most importantly, you can scan and get a picture of the state of the system. And this is something that was not easy to prove asynchronous, but it was done and it got awards for that. And once you have that object, you can actually implement the payment object. Every process stores the sequence of its outgoing payment in a snapshot location. And to pay, you need to know how much money you spent in the past. And this is what the snapshot object helps you with. And if you want to read, you simply scan and return the current balance. So this object can be implemented asynchronously. Nothing in this process, in this journey, is very difficult. Once you know FLP, once you know what is a snapshot, once you know that message passing and shared memory are equivalent, all these pieces are very simple. Of course, the journey, you need to think about it, but you need to think about it, and you would do that if you know distributed computing. So the consensus number of this object is 1. In fact, this means that this object is asynchronous. I don't want to go into the details. What is important here is if you generalize a little bit this object and say, what if instead of having only Alice who can send money to Bob from that account, there could be K processes. You can call that a smart contract with K participant. Then you can prove that the consensus number of this object, of which can be accessed or debited by K processes, the consensus number is K. And again, this is not something very, very complicated. There was a PODC paper last year presented, if my memory is correct, by Matej Pavlovic with Adi Serendici and Petr Kuznetsov and others who have shown this result. So interestingly, not only this exercise helps you understand Nakamoto's paper and actually all those papers, but it also, I believe, helps you come up with better algorithms. So as I pointed out, the shared memory algorithm as presented was published at PODC, but you can also actually build a distributed system which with faster and, most importantly, easier to understand algorithm. So there have been a collection of results and protocols implemented. Once we understood the shared memory algorithm, we took the journey back to message passing and implemented things in a deterministic as well as randomized manner. So this journey to the center of distributed computing, somehow what helped us understand is that what I call that industry, it's not industry, but what those people came up with and what industry leveraged later are actually things we understand very well, to the point that we can improve on the original protocol. So this was one example, payment, distributed payment. In fact, I believe there are other interesting examples. One of them has been very controversial recently, at least in Switzerland. You probably heard about tracing as COVID tracing. There was a big controversy in Switzerland between, first, there was a consortium of researchers, European researchers, trying to build a tracing application, essentially an application running on the smartphone of people, and people who meet each other in a train or in a bus or in a restaurant exchange some identities. They doesn't need to be stable identities. It could be, those could be temporary identities. And if someone gets diagnosis to be sick, then there should be a way to alert the other people who have met the sick person and tell them, you have to go and you got to go check yourself at the hospital. So this is, sorry. This is the tracing application. The controversy was, is the tracing application distributed or not? So distributed was viewed as the holy grail. The European solution was not considered distributed. And then the Swiss solution was considered distributed. But if you look very carefully, none of them was really distributed. Essentially, both solutions, whether the originally European or Swiss, requires some server to host or to log the information of people at some point. If you get sick, there will be this server in a hospital or whatever who will get your information. And then the rest are some subtleties I don't want to go into now. It turns out, and I strongly believe that this is something that the distributed computing community could really work with and come up with a really distributed solution. And there are various protocols that will enable us to understand this application very well. There are gossip algorithms and population protocols. And just to give you an idea, when you have gossip protocols, one of the problems you typically try to avoid is if somebody sends a rumor, you want to hide who sends the rumor initially, the rumor or the virus or the gossip. It turns out that if you inverse slightly this problem, it looks like trying to detect patient zero. Who was the first initiator of the virus? Who was the first person to come from, I don't know where, to Italy and starts the virus in Italy or whatever. And these are things that I think the distributed computing community can contribute with very significantly. I invite you to read a paper by Adrien Hendrix, Aurélien Bellet at this disk. And the population protocol is another model that you will hear about, I think, by Jim on Wednesday. And probably you will see similarities. There are also not only applications that can give some interesting problems, but also, as I pointed out, middleware, also called systems. I suspect many of you have seen these logos. So these are very famous logos these days. Probably if you are only doing failure detectors, local models, or congest models, you don't know what I'm talking about. But if you read a little bit what's going on out there, you might know what these logos are about. So these are PyTorch and TensorFlow, the main tools used for machine learning today. So machine learning is successful because you have a lot of data, but in order to handle this data, the only way is to distribute it. So these are distributed platforms that enable you to do distributed machine learning. Essentially, in those two platforms, there is one computer called the parameter server who owns a model, and then a bunch of workers which participate in the training of the model. And okay, I think somebody's calling me. I don't know what's going on. And sorry, I see something wrong with my. Yuval, can you hear some noise or just me?
No, I hear everything okay. I mean, Only hear
Okay,
you,
good,
which
good.
is good.
So it's maybe just me. Sorry, I apologize about that.
No worries.
So in that distributed machine learning model, every computer is supposed to work perfectly well. And as we all know, these things don't match reality. And even the designers of those platforms, either PyTorch or TensorFlow, by the way, Facebook or Google, realize that failures are the norm. And now that machine learning is used in many important applications, critical applications, so it's clearly a place where we want to understand what happens if failures occur. We want to build protocols that are fault tolerant, and the Byzantine model is great. So maybe 5 or 6 years ago, people started looking at this very carefully with the lenses of distributed computing, with the distributed computing lenses. So I won't tell you the full story. I simply invite you to read a PODC paper that will appear in this edition, and a companion paper on a different model on archive, as well as a couple of SRDS papers. Essentially, all this work consists in looking at those platforms and trying to ask the question, how can we make them Byzantine resilient? And there are a bunch of PhD theses there that have been achieved. One of them just finished by Mehdi Hamdi, and I invite you to read that work because I believe it's another example where a journey to the center of distributed computing helped improve something that, and maybe even might have some impact on industry. Actually, it's not only having an impact on industry, it's also having fun. I mean, these problems are really interesting. I have worked myself on weakest failure detectors, and I don't think these problems are less fun than weakest failure detectors. This exercise of taking problems from industry and trying to take them to the center of distributed computing also sometimes help correct some misunderstanding and some folklore. I'm just mentioning some of them. And this is the work that I'm summarizing in one slide by Carlos Antoniadis. Just to give you one example, the fact that you might have heard of the CAP theorem. So the CAP theorem is something that people in industry, or at least in some industries, seem to appreciate. The CAP theorem says, if you want to build a highly available system and you replicate your information, you cannot at the same time have consistency or linearizability and have partitions. And this basically have led people to look for alternative consistency criteria, and they discovered that there was something called causality. Okay, the old causality notion of Lamport has been discovered recently. And people thought that in order to build a highly available distributed system with replication, causal transactions are great. And with causal transactions, you can solve the world. In fact, a lot of papers have been written about that, and they actually contain many interesting mistakes. I call them interesting mistakes because most of the time things work. But if you look very carefully, you realize that actually causal transactions, they might eventually terminate, but they're not fast at all. And they're not practical, unlike what is claimed. But this requires some journey to the center of distributed computing. Okay, let me finish by looking at the other part, which is hardware. I told you earlier that a lot of the work in this field came up with Dijkstra trying to build a multiprocessor operating system in 65, and then coming up with atomicity and registers and P and V primitives, etc. It turns out that we can still play a similar exercise in the sense that we can leverage what hardware people are coming up with and try to improve on matters and get interesting problems to work on. I'll just mention a couple. RDMA. So what is RDMA? I told you earlier that we view the world as either message passing or shared memory. So this distinction is something we have been living with for decades. The new technology or the new hardware that some companies are coming with is essentially bringing or mixing the two. So intuitively enabling one machine or one computer to read or write directly in the shared memory of another computer without sending messages. Even more, there is this idea of protecting a memory by some sort of optimistic lock. I'm simplifying things. So this kind of technology or hardware is somehow bringing or narrowing the gap between message passing and shared memory. And I think it poses interesting problems for distributed computing. And if we look again into that kind of technology with the lenses of distributed computing, we can come up with interesting results. So for example, and this is some work with Igor Zablici and Naama Ben David and Marcos Aguilera and others. I'm sorry, I'm forgetting some. Virendra Marathe. You can show, for example, that you can solve crash-stop consensus with 2f+1, with f+1 instead of 2f+1, and you can solve Byzantine resilient consensus with 2f+1 instead of 3f+1. So of course, it's the kind of results that we like to have in PODC and disk. We like to show, for example, that you only need 2 steps instead of 4 steps. But furthermore, you can actually leverage these kinds of theoretical results and actually build the system. And the people I mentioned, especially the students, because usually they are the ones who do the work, they actually built a system called Mu where they can show that they can solve consensus in 1 microsecond. And I think that's pretty interesting to go back and build a system using those results. The other example, and this is going to be, I think, the last one, is NVRAM, or persistent memory. So here, the idea is to say, instead of having objects that we can read and write, and when the machine crashes, we forget about them, the objects are persistent, and they have some notion of persistent fence. A persistent fence is like a fence where you can write in disk in order to, when you recover, quickly catch up and continue the computation. And I think, again, here, the problem that you can pose are as interesting as the classical problems we used to play with. For example, the very notion of linearizability in this context need to be revisited, and some people have done that pretty well, and even come up with new bounds on how many persistent fences you need per operation. So this is the work of Igor that I mentioned already with National Cohen. Okay, so let me conclude with my main message. The rise and fall of distributed computing. So what I wanted to say here is that for those of you who missed the beginning of my talk, distributed computing is everywhere, which is a fantastic chance for engineers who took a master in distributed computing. But it's also a danger for the research in distributed computing, especially the theoretical one, because there is this risk of being isolated and somehow having fun maybe, but not having any impact, which is fine. Not having any impact in industry, which is fine if we just want to have fun. But students usually don't only want to have fun, they also want to have jobs and funding. And my suggestion is really to look at the problems that are coming, or innovation that is coming outside of the field of research, because I believe most of the interesting, or at least most of the innovation, is coming from industry, and try to take those innovation to the center of distributed computing and maybe come back with better solutions. And I insist that there should not be any snobism there. It's not a shame to do that exercise. And that exercise has been done and has given birth to the most interesting results we have in our field and in our community. So I just want to mention a bunch of students who have been working on these trips, and I thank you for your attention, and sorry for the slight mess. I'm not used to this kind of talks on Zoom with the noise and the camera on and off. Thanks, Yuval, for the great work.
Okay, thank you very much, Rachid. Again, virtual clapping our hands. We do have time for questions, so please go ahead, use the raise hand function in Zoom. Okay, Nitin, let me allow you to unmute yourself. Nitin.
Hi, Rachid. Great talk. So I think your message was for the researchers, and I agree with the message. The question for you is, what should the conference do? What should PODC do as a community or the conference or desk? How do we sort of encourage this kind of work appearing, more rapidly?
Thank you very much, Nitin. Well, it's hard to talk to a conference because the conference is a bunch of people, but the only thing I see, which seems obvious to me, is stop considering irrelevant problems that have not been posed in previous editions of the same conference. I think we have this tendency. If a problem is coming from elsewhere, we tend to consider the problem as irrelevant. And I have seen that on many occasions, and I think it's a mistake. So that's one obvious thing to me. So we have to be open-minded, and open-minded does not mean we need to accept anything, but at least the problems, the way they come, the way they're phrased might be sometimes different. That's one obvious thing that I've seen.
Okay, Adam, I think that Adam had a question. Just a second. Okay, Adam, you can unmute yourself. Oh, sorry.
Yeah, thanks.
Okay, yeah.
Again. So thank you for the talk. So I do think it's actually a very interesting take, because they're saying we should look at industry and see how we can sort of rephrase or understand the innovation from industry using the theory. Do you think it can also apply to things that are not necessarily from the theory, but for example, to biological systems, to social situations, to things like that, to apply distributed lens to them?
Well, I'm not experts there, definitely not. I'm not saying I'm expert in industry either, but there I'm even less expert. So I have a hard time saying what can be done there. Now, there have been people who have been doing that kind of work. If you look at Bernard Chazelle, for example, I think his work is amazing in that direction. And if you hear French, you should go to his leçon inaugurale at Collège de France on the topic. It's really amazing. And he has also some talks on the topic. Nancy has also done some work in that area. With I think Yuval has also done some work in that area. So there are, I think, many work in that area, but I can hardly say anything more than that.
Gadi? Wait a minute.
Hi, Rachid, I enjoyed the talk. So you gave 4 examples of problems that you can take them to the center of distributed computing. Any other problems that people have not been working on yet, doing the same journey? Just starting points?
Well, so the tracing application is something, and some of my some people will be upset with me, I'm sure, but that's, I think, an interesting problem that nobody has taken yet. But that's just one example. So nobody has really published anything on that. And I think the controversy there is something that the PODC community could help solve and help explain what is really a distributed solution, what is not distributed there.
Yeah, the resemblance of this problem to the population protocols model is quite remarkable, right? It's okay, Jennifer?
Hi, thanks, Rachid, for the talk. I don't know very much at all, or really anything about distributed machine learning, but I was wondering if you could say a couple more words about that. And also, if you think the distributed computing community could have any kind of particular insights on things that might address some of the kind of negatives that we've been hearing about in the news about, unfair AI and things like that.
Yeah, Okay, I invite you to come to the talk of, I think, Arsani Girgis and Sébastien Rouault are going to give the talk this week. And you might ask them and they might have better answers that I'm going to give. Or you directly address the question to my co-authors, Mehdi and Lee. Now, I think definitely, I would say definitely, because of course you can consider the extreme case of nodes that have been controlled by an attacker and model that as a Byzantine failure. And I think there, what is interesting is that the number of papers in MIPS and ICML on that topic is just amazing, exponentially growing. People are discovering the Byzantine failure model. And it's pretty interesting to see how the adoption of the language we have been using in those communities without us somehow being aware that that work exists. And I think Nitin has been working on that. Nadim Hamdi, Layad, people, I mean, listening have been working on that. But furthermore, I even think there is still a huge opportunity of work. As I tried to point out, so far people have been assuming the case where you have one central server and a bunch of workers that can be Byzantine. But once you remove that assumption, I think a lot of things are really interesting. Modeling the problem as an agreement problem is something interesting. Of course, I'm saying interesting. I have been working on that with some colleagues and students, but I think that the field there is amazing. And if you go to weaker failure models by saying the adversary might not be Byzantine, but can only do this or that, I think there you might be addressing exactly the question you're asking of unfairness. You can even use some game theory to model the unfairness precisely. And again, people in this community have been doing a lot of work on game theory in distributed context.
Thank you.
Mm-hmm. Gadi, is that another question, or you just forgot to lower your hand? Gadi, do you have another question?
He says no.
He says no. Okay. So I'll lower his hand. Any more questions? You can raise your hand virtually, or you can. Eli Gaffney has a question, I think. Eli? Just a minute. Let me try to unmute Eli. Just a minute. I have to find Eli in order to unmute him. Usually people are trying to mute Eli. Now I'm trying to unmute Eli. So
I think Zoom doesn't want you to unmute Eli.
Apparently. Just a second. Okay, good. Unmute.
Okay, thank you. You hear me now?
Yeah.
Yeah. First of all, as everybody, thanks for the talk. First about the title, and then the topic, the top of this slide, journey to the center of the earth. Immediately, I thought about the opposite. You know, that we are unseen. I thought immediately about 20,000 nautical miles under the ocean. And the rise and the fall, it's usually, most people probably associated with Rome, but to me, it's a book of William Schurer, The Rise and the Fall of, I would say that even the name that he told before, of Germany. So I just wanted to comment about the timing. I think the analogy is, you know, that you are saying relevant and irrelevant, and you know, the timing of people who are late in their career should do theory sort of, and people in the beginning should do the application. I think it's the opposite. It's extremely hard and very hard to discern whether you have real innovation when you do application, or whether you are doing just technologies transfer. And I must say, you know, there is a controversy that theory people say that applicative people reject their paper and vice versa, like we have with the combinatorialist. I think that early in your career, you should do the theory, because I claim we still don't understand distributed computing. I still think there is so much to understand. The simplest questions are still not answered. And therefore, I would say the opposite when you get to the end of your career, or not to the end, let's say, then it's the time for applications. To me, the theorist, usually when I see many applications, and that's why I don't sit on many PhD committees, because my question always is, before you went to sleep, what did you think about? Which is the way I work. I think before I go to sleep, and hopefully when I wake up, there is a solution. It happens once half a year, but so let's you just now discuss the trade-off between application and theory, and I agree with you that perhaps we don't have enough applications that from the outside we don't look that let's call it sexy, but I think we are, and I support you, but I just think about the timing being different, that early in your career is where we should be first, and then move to the application.
Thank you. I get from the silence that the question is over.
Yeah,
that's my understanding. Okay. Thank you, Eli. I think there is a misunderstanding here. I'm not opposing theory with practice. I'm really talking about PODC and theory. I'm simply saying there are different kinds of problems you can address when you do theory. You can, and I use this example because I did my tenure on that. You can work on the weakest failure detector problem. That's an interesting theory problem. But you can also work on other problems that are not easier, intellectually easier. And you can even have fun, but they require the curiosity to go out and pick them from elsewhere. You can pick some interesting problems from the PODC community and stay with the PODC community, but you can also take problems from outside and bring them to the PODC community. And it doesn't mean that they're not theory. They can be hard theoretical problems. It's just that you are bringing them from outside to the center of distributed computing. But I completely agree with you, but there are fascinating problems to be solved in distributed computing. I did not claim to have the solution. I simply said, why not do that as well? And there is no shame in doing that. This is what the people who defined the field have done in the past. That's what I'm saying. But of course, the robustness of the hierarchy or other problems are interesting. And I'm sure in the local and context models, there are fascinating problems. I'm convinced.
Okay, Christoph?
Hi. You said that we should go forth and bring some problems. So do you think it also makes sense to tell the world that they can bring problems to us, like maybe having an option of submitting open problems, or having a session where people could present their distributed problems without having research paper or solution in a traditional PODC style?
Yeah, I think it's a good idea. Whether they're going to do it or not is because these people who have interesting problems from industry are very, very busy themselves. So asking them to bring their problems to us is a way of telling them, look, we are going to solve your problems. And usually they believe they can solve them themselves and they are not going to pose them. But of course, if they're willing to, I think that would be fantastic. But I really think we have to do the job ourselves. We have to go ourselves and listen to other problems and try to crystallize the problem in our language and maybe do the exercise ourselves.
I think that we are bringing in most PODC and DISC meetings that I remember, at least one of the invited speakers was supposedly coming from industry and was supposed to bring their exciting new problems. I'm not saying that it always works, but there are such attempts, right?
Yeah, absolutely. Yes, there are some such attempts, but I think in my opinion, we have to do the effort. It's not going to come for free. That's my experience.
Mm-hmm. Next question, I think Istvan.
Hi, yeah. Can you hear me?
Yeah.
Yeah. So I just wanted to jump in on that, and actually, as a complete outsider to the community, just to say that perhaps ways of achieving this is to also cross-pollinate, and for instance, Eurosys is I think a place where you have many researchers who are working kind of 1 feet in the distributed let's say theory field, and also in the more applied aspects of it. And things like proposing workshops or trying to bring some kind of showcase of the cool stuff going on in PODC to a place like Eurosys could bring that kind of dialogue ahead, because I feel I'm working on the other side of things, more on the application side, right? And I feel that there's a lot of very, very interesting insights going on in your community, and I'm one of those people who, by Rachid's description, is indeed flabbergasted by the by this nice proofs of synchrony or asynchrony and converting within the problems. And I think having more dialogue across communities would be useful. So this is my plug to say that Eurosys is accepting workshops, and me as one of the workshop chairs, I definitely invite people from this community to actually come and submit a workshop proposal, and perhaps start the ball rolling so that we can kind of discuss interesting intersections.
Yeah, thank you very much. Next question, Michael.
Okay, I'm unmuted now. I very much support this idea of looking at the real world problems and then trying to apply theoretical methods to it. Certainly the FLP paper resulted from that, and as did the population protocols. But in both cases, the first step that has to be done, and it turns out, from my experience, is maybe the most difficult one, is to come up with a precise model of what it is that the application is trying to do. And as the applications get more and more complicated, the problem of modeling becomes more difficult. I think the Bitcoin is a good example of how finding the right model really is difficult, and that in the real world, the transactions have to complete in a certain amount of time. So we can't get away from the notion of time, and how we even want to deal with partitions of the internet is a very real problem. And how we want to deal with issues of trust, which is the Nakamoto paper talks heavily about trust. But there are so many things that we have to trust in any real cryptocurrency system. We have to trust the internet. We have to trust that the DNS is giving us the right answers. We have to trust that we can find the Bitcoin servers. How do we do that? We ask Google. Well, then we have to trust that Google is giving us correct information. So the whole idea that the goal of the cryptocurrencies is to eliminate trusted third parties seems to me to be destined to failure right from the beginning. But how do we prove that until we have some really good models? So I think this is an area that there's a lot more work to be done.
Can't agree more. Thanks, Michael.
Okay, just a second. Krishna Yerev.
Unmute, yes. Yes, I'm Krishnamurthy Iyer. Yes. So you were talking about cross-pollination from different fields, right? My PhD was in information theory, and in information theory, the multiple access channel, that is you have two senders and one receiver, was solved in 1970. The distributed multiple access channel was the first problem I studied in my PhD thesis, and that was done in around 2010. So the moment many interesting problems in telecommunication networks, the moment you recast them in a distributed framework, that is, there's not enough centralized information, they become immensely more rich and interesting. Just want to say this. Just to add this.
Yeah, thank you very much. The funny part is that today, most interesting problems are already cast in a distributed fashion. It's just that we don't look at them yet. I hope we will do that before we disappear.
Right. Thank you, sir. Thank you.
Okay, any more questions? Please virtually raise your hand or use the chat. Okay, so I think that we can break this first session at this point. We'll be happy to see, I didn't check the Zulip domain in the last couple of hours, but we'll be happy to see more discussions over there. Rachid, thank you very much.
Thank you, and sorry for the confusion with the format, but next keynote talk I will do much better with this Zoom stuff. Thank you very much.
No worries. So thank you everybody again. Please, we are maintaining this meeting, so don't go anywhere. You can go and you should come back. This meeting will stay open until the next session starts, which is in roughly 28 minutes. So bye for now. Again, this meeting remains open. And Luis, we can use the private chat again, and I will pass you the host control soon, okay?